Good morning, everyone. Before we even touch the chalk, pause for a moment and look at the heading on the board. Real numbers. Now, I want you to ask yourself one honest question. What is mathematics made of? Not formulas, not tricks. It is made of numbers. That is why this chapter is not just chapter 1 in the book. It is chapter 1 of your mathematical thinking. Every topic you will study later, polynomials, geometry, trigonometry, stands on the rules we learn here. If your foundation is strong, the building will never shake. You can see the checklist on the board. These are not random topics. The fundamental theorem of arithmetic tells us why numbers have a unique identity. Highest common factor and lowest common multiple teach us how numbers cooperate in real-life situations. And the proofs of irrational numbers train your brain to think logically, not emotionally. Yes, this chapter carries 6 marks in the board exam, but more importantly, it carries confidence marks for the rest of Class 10. So, take out your notebook. Today, we don't rush. We build. Now, look closely at this number line. Don't look casually. Look like a mathematician. Earlier, you thought numbers were just 1, 2, 3, 4, neat and clean. But mathematics grew up. Between 1 and 2, do you see empty space? No, there are infinitely many points. Decimals like 1.5, 1.25, 1.333, and roots like square root of 2. This entire unbroken line is called the set of real numbers, written as R. Why do we call them real? Because every number that can exist on a measuring scale belongs here. Length, weight, temperature, nothing falls outside this line. And here is a very important board exam statement. Real numbers equals rational numbers plus irrational numbers. No gaps, no holes, no missing values. This idea will be crucial when we talk about irrational numbers later. Remember this picture. Let's go back in time, thousands of years ago. Humans began mathematics not with formulas, but with counting. 1 cow, 2 goats, 3 bags of grain. These counting numbers are called natural numbers. They always start from 1. But then a very important question arose. What if there is nothing? If you have no apples, how do you write that? That is why 0 was invented, one of the greatest discoveries in mathematics. When we add 0 to natural numbers, we get whole numbers. Now, be very careful. Every natural number is a whole number, but 0 is not a natural number. In exams, many students lose marks here by writing wrong sets. Remember the picture. N sits inside W, but 0 stands only in W. Now, numbers learn direction. If I say 5, it could mean 5 rupees in your pocket. But what about 5 rupees debt, or 5 degrees below 0? That is where integers come in. Integers include positive numbers, negative numbers, and 0. The symbol Z comes from the German word Zahlen, meaning to count. Important exam logic. Every whole number is an integer, but negative numbers are not whole numbers. So if you ever see -3 inside whole numbers, that is a 100% mistake. Think of integers as whole numbers with a sign board, plus, minus, or neutral. Now comes a very important family, rational numbers. The word rational comes from ratio. Any number that can be written as a fraction of integers belongs here. But look at this condition carefully. Q not equal to 0. Why can't the denominator be 0? Because division means sharing. You can share 5 apples among one person. You can share them among 5 people. But can you share among 0 people? It has no meaning. That's why division by 0 is undefined, not just wrong. Also remember, -5 is rational because it is -5 over 1. 0.75 is rational because it is 3/4. This point appears often in MCQs. Now meet the rebels of mathematics, irrational numbers. These numbers refuse to behave. Their decimals never end, never repeat. Take square root of 2. The digits go on forever without any pattern. Take pi. Scientists have calculated trillions of digits and still no repetition. These numbers cannot be written as p over q. Why are they important? Because without them, the number line would have tiny gaps. Irrational numbers fill those gaps, making the real number line complete. Later in this chapter, you will prove that these numbers cannot be rational, not guess, but prove. Now we come to the most important idea of the chapter, prime numbers. A prime number has exactly 2 distinct factors, 1 and the number itself. Now, listen carefully. This is a classic board trap. Why is 1 not prime? Because it has only 1 factor, not 2. Why is 2 the only even prime? Because every other even number is divisible by 2, giving it more than 2 factors. Think of primes as atoms. Just like atoms build molecules, primes build all numbers. This idea leads directly to the fundamental theorem of arithmetic. If primes are bricks, then composite numbers are buildings. Any number greater than 1 that is not prime is composite. Our job as mathematicians is to break buildings back into bricks. This process is called prime factorization. Why do we do this? Because once a number is broken into primes, it reveals its true identity. Every HCF, LCM, and proof in this chapter depends on this idea. Before the theorem, meet the mind behind it. Carl Friedrich Gauss was so brilliant that mathematicians called him the Prince of Mathematics. He proved something revolutionary. Every number has a unique identity made of primes. Just like your fingerprint identifies you uniquely, a number's prime factorization identifies it uniquely. This idea was formally proved by Gauss, and it changed mathematics forever. This theorem is not just theory, it is power. It says every composite number can be expressed as a product of primes, and this factorization is unique apart from order. Why do we say apart from order? Because 2 times 3 and 3 times 2 are the same multiplication. But here is the key idea. The primes used can never change. No matter how you factor a number, you will always end up with the same primes. This theorem is the spine of this chapter. Every major question, factor trees, highest common factor, lowest common multiple, irrational proofs, stands on this one idea. Before we move on, ask yourself, do I understand why uniqueness matters? If yes, excellent. If not, don't worry. We will see it again, very clearly. Now pause here. This slide answers a very important why question. Why does the theorem insist on the word unique? Think about fingerprints. 2 people may look similar, but no 2 fingerprints are the same. In the same way, prime factorization is the fingerprint of a number. Let's take 30. I break it carefully. 30 divided by 2 equals 15. 15 divided by 3 equals 5. So 30 equals 2 times 3 times 5. Now, listen very carefully. There is no other combination of primes in the entire universe that will multiply to 30. You can change the order. 3 times 5 times 2. 5 times 2 times 3. But the ingredients never change. This uniqueness is why HCF works, LCM works, and proofs of irrational numbers work. If factorization were not unique, mathematics would collapse. That's why Gauss's theorem is called fundamental. Now, a very common student doubt. Sir, is 7 times 5 times 3 times 2 wrong? No, mathematically it is correct. But exams demand standard language. In mathematics, we follow a discipline. That discipline says, always write prime factors in ascending order. Why is this important? Imagine two students. One writes 2 times 3 times 5 times 7. Another writes 7 times 3 times 2 times 5. Comparing becomes messy, so we fix a rule. 2 first, then 3, then 5, then 7, then etc. This standard form avoids confusion and prevents silly mistakes in HCF, LCM questions. In board exams, clarity equals marks. Now comes the number that scares students: 32,760. Before panic, remember this. Large numbers don't require courage, they require method. Step 1. Always check divisibility by 2. Why? Because 2 is the smallest prime. 32,760 ends in 0, so it's even. We divide calmly. Look how beautifully the number reduces. 1 2 comes out, then another, then another. We continue as long as the number is even. Important exam tip: don't jump primes. Finish with 2 completely before moving on. This patience saves marks. Now we have reached 4,095. Ask yourself, is it even? No. So we test 3. How do we test 3? Here we use sum of digits rule. 4 plus 0 plus 9 plus 5 equals 18. 18 is divisible by 3, so 4,095 is divisible by 3. Now, a very important warning. Students often confuse sum of digits with sum of exponents. This is only a divisibility test, nothing more. We continue. 4,095 divided by 3 equals 1,365. 1,365 divided by 3 equals 455. 455 ends in 5, so divisible by 5. 455 divided by 5 equals 91. 91 equals 7 times 13. Now stop. Why? Because 7 and 13 are primes. Every branch of the tree has ended in a prime. That means the factor tree is complete. Never stop early. Composite numbers must be fully broken. Now we collect the prime bricks. Count carefully. How many 2s? 3. How many 3s? 2. 1 5, 1 7, 1 13. So we write 32,760 equals 2 to the power of 3 times 3 to the power of 2 times 5 times 7 times 13. This is not decoration. This is the DNA code of 32,760. According to the fundamental theorem of arithmetic, no matter how you draw the tree, no matter which path you choose, you will always reach this exact code. This guarantees correctness in exams. In board exams, time is your biggest enemy. You cannot afford long division everywhere. Look at 5005. Is it even? No, so skip 2. Sum of digits equals 10, so not divisible by 3. Ends in 5, so divisible by 5 immediately. This is not shortcut cheating. This is mathematical intelligence. Divisibility rules are like shields. They protect you from wasting time and reduce calculation errors. Use them confidently. This question looks simple, but tests conceptual clarity. For a number to end in 0, what must it have? A factor of 10, and 10 equals 2 times 5. Now, break 4. 4 equals 2 squared. So 4 to the n equals 2 to the 2n. Ask yourself, where is the 5? No matter how large n is, you will only get 2's, never a 5. By fundamental theorem of arithmetic, a missing prime can never appear magically. So the answer is 4 to the n never ends in 0. This exact logic is expected in 2 to 3 mark answers. Now apply the same logic. 6 equals 2 times 3, so has 2, no 5. 15 equals 3 times 5, so has 5, no 2. Ending with 0 needs both. So 6 to the n never ends in 0. 15 to the n never ends in 0. This is the power of structure over calculation. No tables, no expansion, just prime logic. Students often make a big mistake here. They calculate the entire expression. Never do that. Look at 7 times 11 times 13 plus 13. What is common? 13. Factor it. 13 times 7 times 11 plus 1 equals 13 times 78. Now, stop. Why is this composite? Because it is written as the product of two integers greater than 1. That is the definition of composite. Board examiners love this reasoning. Same idea, different appearance. 7 times 6 times 5 times 4 times 3 times 2 times 1 plus 5. Students panic seeing so many numbers. But stay calm. Look for common factor. Both terms contain 5, so factor it. 5 times 7 times 4 times 3 times 2 times 1 plus 1. Now the number is clearly a multiple of 5 and greater than 5. Therefore, it has factors other than 1 and itself. Therefore, it is composite. Zero heavy calculation, full marks logic. Now, listen very carefully. HCF is not generous. HCF is extremely picky. When we find HCF, we ask only one question. What do these numbers share in common? Not what is big, not what looks impressive, only what is common. And even among common primes, we are strict. If one number has 2 to the 4th and the other has 2 to the 2nd, the HCF can take only 2 to the 2nd. Why the smaller power? Because HCF must divide both numbers exactly. Think of HCF like shared land. You can only claim land that belongs to both owners, and only as much as the poorer owner has. This logic prevents 90% of HCF mistakes. Now meet HCF's opposite cousin, LCM. LCM is not picky at all. LCM is greedy. It asks, what is the smallest number that can contain both numbers completely? So what does it do? It takes every prime factor that appears anywhere. Always chooses the highest power. Why highest power? because smaller powers might fail to include one of the numbers. Think of LCM as the biggest box needed to fit all items. HCF looks for overlap. LCM looks for coverage. Never mix these two ideas. Let's apply the rules calmly. First, factorize properly. 6 equals 2 times 3. 20 equals 2 squared times 5. HCF. Common prime equals 2. Smallest power equals 2 to the 1. So HCF equals 2. LCM, take everything. Highest power of 2 equals 2 squared. Include 3, include 5. So LCM equals 2 squared times 3 times 5 equals 60. Now notice an important check. HCF divides both numbers. Both numbers divide the LCM. This relationship is not accidental. It is structural. This formula is pure gold, but only if you use it correctly. For two numbers only, this always works. HCF times LCM equals product of numbers. Why does this work? Because HCF takes the minimum powers, LCM takes the maximum powers. Together, they reconstruct the full prime power of both numbers. But listen carefully. Warning: this rule fails for 3 or more numbers. Using it blindly is one of the most common board mistakes. Use it as a shortcut, a verification tool, but never beyond 2 numbers. Let's verify the rules step by step. First, factorize. 26 equals 2 times 13. 91 equals 7 times 13. So, HCF equals 13. LCM equals 2 times 7 times 13 equals 182. Now check. 13 times 182 equals 2366. 26 times 91 equals 2366. They match. This is how a careful student checks answers in exams. Verification gives you confidence and saves marks. Before solving any word problem, do not calculate immediately. First, decode the language. Ask, are we dividing into maximum equal parts? HCF. Are events happening together again? LCM. If you misidentify this step, even perfect calculation gives 0 marks. This table is your compass. Always decide the method before the math. 616 soldiers and 32 band members must march in the same number of columns. What does same number of columns mean? Dividing both groups equally. Do we want maximum or minimum columns? Maximum, so that columns are as wide as possible. That word maximum screams HCF. So we find HCF of 616 and 32 equals 8. Hence, 8 columns. This is a textbook HCF problem. Language equals logic equals formula equals answer. Sonia takes 18 minutes, Ravi takes 12 minutes. They both start together. When will they meet again at the starting point? This is not division. This is synchronization. Whenever things repeat together, we use LCM. LCM of 18 and 12 equals 36. So after 36 minutes, both return together. Remember, speed differences equals LCM. Repetition equals LCM. This logic applies to clocks, bells, lights, everything.
3 lights change every 48 seconds, 72 seconds, and 108 seconds. They flash together again after their LCM. Calculate carefully. LCM equals 432 seconds. Now convert. 432 seconds equals 7 minutes, 12 seconds. Start time equals 7 a.m. So next synchronization is 7:07:12 a.m. Board exam warning. Many students forget to add the time to the start clock. That costs 1 full mark. This is a classic trap question. If a number leaves a remainder, it means it is not divisible by the required divisor. So, what do? We remove the remainder first. Given 70 leaves remainder 5, actual divisible part equals 65. 125 leaves remainder 8, actual divisible part equals 117. Now we find HCF of 65 and 117 equals 13. Never take HCF directly when remainders are involved. Always clean the numbers first. This single idea can save you 2 to 3 marks.
Now we practice what we've learned. First rule, never guess HCF. Always factorize. Let's go one number at a time. 96. Divide by 2, 48. Divide by 2, 24. Divide by 2, 12. Divide by 2, 6. Divide by 2, 3. So, 96 equals 2 to the 5th times 3. Now, 404. It's even, so divide by 2, 202. Again, even, so divide by 2, 101. 101 is prime, so 404 equals 2 squared times 101. Now comes the HCF rule. Take only common primes and take the smallest power. Common prime here is 2. Powers are 2 to the 5th and 2 squared. Smaller power is 2 squared. So, HCF equals 4. Notice 3 and 101 are not common, so they are completely ignored. This is where many students go wrong. Now, instead of doing another long factorization, we use the duo rule. We already know HCF equals 4. Numbers are 96 and 404. So, LCM equals 96 times 404 divided by 4. First, simplify. 96 divided by 4 equals 24. Now, multiply. 24 times 404 equals 9,696. So, LCM equals 9,696. Quick sanity check. LCM must be divisible by both numbers. 9,696 divided by 96 equals exact. 9,696 divided by 404 equals exact. Everything fits. Answer is correct. Now comes an important change, 3 numbers. Whenever the count increases, HCF becomes stricter. Factorize all 3. 12 equals 2 squared times 3. 15 equals 3 times 5. 21 equals 3 times 7. Now ask one question. Which prime appears in all 3? Only 3. 2 appears only in 12. 5 appears only in 15. 7 appears only in 21. So they are rejected. Hence, HCF equals 3. Key exam line. A prime must be present in every number to be part of the HCF. Now we find LCM of the same three numbers. Rule changes completely. LCM asks what is the biggest power of every prime appearing anywhere. From factorizations, highest power of 2 is 2 squared. Highest power of 3 is 3 to the first. Include 5, include 7. So, LCM equals 2 squared times 3 times 5 times 7. Calculate, step by step. 4 times 3 equals 12. 12 times 5 equals 60. 60 times 7 equals 420. So, LCM equals 420. Now, a very important warning. Do not apply the formula HCF times LCM equals product for three numbers. It fails here, and the board loves asking this trap. Arnav has 40 centimeters red ribbon, 84 centimeters blue ribbon. He wants the maximum equal length pieces. Underline the word maximum. Whenever you see maximum, greatest length, equal pieces, you must use HCF. Now find HCF of 40 and 84. Factorize. 40 equals 2 cubed times 5. 84 equals 2 squared times 3 times 7. Common prime is 2. Smallest power is 2 squared, which is 4. So each piece is 4 centimeters. Units are important. Never forget them. A rod must measure all three dimensions exactly. That means the rod must divide all lengths perfectly. This is a classic HCF situation. Lengths are 825 centimeters, 675 centimeters, 450 centimeters. After factorization, the common primes give HCF equals 75. So, the longest possible rod is 75 centimeters. Why not smaller rods like 1 centimeter? Because the question asks for the maximum possible length. Language decides the method. Smallest number divisible by both is a direct signal. This is LCM. No debate. We want the first meeting point of both numbers. After proper factorization and combining highest powers, we get 21,252. Important exam tip. Do not write explanation like a story. State clearly, required number equals LCM of given numbers. Bells ring every 6 minutes, 12 minutes, 18 minutes. They ring together again after their LCM. LCM of 6, 12, 18 equals 36. So, bells ring together every 36 minutes. Starting at 6 a.m., next time is 6:36 a.m. Always write interval result and final clock time. Both are expected. There are 420 Kaju burfis, 130 Badam burfis. We want tallest stacks with equal number in each. Tallest stacks equals maximum per stack equals HCF. HCF of 420 and 130 equals 10. So each stack has 10 burfis. Stack height comes from HCF logic. Participants are 60, 84, 108. They must be seated with same subject, same number per room. To minimize rooms, we must maximize participants per room. That means HCF. HCF of 60, 84, 108 equals 12. Now divide 60 by 12 equals 5. 84 divided by 12 equals 7. 108 divided by 12 equals 9. Total rooms equals 5 plus 7 plus 9 equals 21. This is a two-step logic problem. 1. Use HCF. 2. Then count rooms. Missing any step costs marks. This is a thinking question, not a factorization question. We are not given the numbers, we are given their product and HCF. Now recall the golden rule for two numbers only. HCF times LCM equals product. So substitute calmly. 12 times LCM equals 1800. Divide both sides by 12. LCM equals 1800 divided by 12 equals 150. That's it. No trees, no prime factorization, just conceptual clarity. Board exam tip. These are usually 1-mark or 2-mark questions. Do them fast and clean. Now this is a trap question. Many students lose full marks here. Given. HCF equals 18. Product equals 3042. Using the same rule, LCM equals 3042 divided by 18 equals 169. Now stop. Do not rush to the answer. Ask a logical question. Must HCF divide LCM? Yes, always. Now check. 169 divided by 18 equals 9.38, etc., not an integer. That is impossible. If HCF does not divide LCM, then such numbers cannot exist. Final answer. No such pair of numbers is possible. This tests logic maturity, not calculation. Students often ask, "Sir, why can't we use the product rule for 3 numbers?" Let's test with a simple example. Numbers 2, 4, 8. Now calculate. HCF equals 2. LCM equals 8. So HCF times LCM equals 16. But actual product, 2 times 4 times 8 equals 64. They are not equal. Why does this happen? Because when more than 2 numbers are involved, common prime factors get counted multiple times in the product. The balance between minimum and maximum powers breaks. Conclusion, very important for boards. The formula HCF times LCM equals product only works for 2 numbers. This is a reverse thinking question. Instead of breaking a number down, we are asked to rebuild the tree. Given relationships guide us. Start from the top. If x equals 5 times 2,783, then x equals 13,915. Now move step by step. Y equals 2,783 divided by 253 equals 11. Z equals 253 divided by 11 equals 23. Now check. Are all final leaves prime? Yes. 5, 11, 23. That confirms correctness. Board exam tip. Always verify the final leaves in a factor tree. If even one leaf is composite, your answer is wrong. This is a very common silly mistake question. Question. Find the sum of exponents, not digits. First, factorize. 196 equals 14 squared equals 2 times 7 squared equals 2 squared times 7 squared. Now read the question again. Exponents are 2 and 2. So sum 2 plus 2 equals 4. Common mistake. Writing 1 plus 9 plus 6 equals 16. Always factorize first. Always read the question twice. Now let's take a bigger number. Same logic. Break smartly. 1800 equals 18 times 100. Now factorize. 18 equals 2 times 3 squared, and 100 equals 2 squared times 5 squared. Combine. 1800 equals 2 cubed times 3 squared times 5 squared. Now identify exponents. 3, 2, 2. Sum 3 plus 2 plus 2 equals 7. Think of this as how many prime bricks were used in total. This is your built-in error detector. Always remember, HCF divides LCM. Why? Because HCF divides number divides LCM. So if HCF equals 18 and LCM equals 380, check. 380 divided by 18 equals 21.1, etc. Impossible. That means either HCF is wrong or LCM is wrong. In exams, this check can save you from negative marking in MCQs and full loss in numericals. If two numbers have HCF equals 1, they are called co-prime. That means they share no prime factors. So their LCM becomes very simple. LCM equals product of numbers. Example, 8 and 9. HCF equals 1. So LCM equals 8 times 9 equals 72. Why does this work? Because nothing overlaps. Everything must be included. Ratio questions test number sense, not factorization. Given, ratio equals 5 to 11. HCF equals 7. Important idea. Ratio is always in simplest form. So actual numbers are 5 times 7 and 11 times 7. Calculate. 35 and 77. Think of ratio as a blueprint. HCF is the scale factor that enlarges it. Now the reverse situation. Given, ratio equals 2 to 3. LCM equals 180. Let the numbers be 2x and 3x. Now find their LCM. Since 2 and 3 are co-prime, LCM of 2x and 3x equals 6x. Set up equation. 6x equals 180 implies x equals 30. So the numbers are 20 and 30. And notice something beautiful. X itself is the HCF. This shows how algebra and arithmetic connect.
Before we prove irrational numbers, we need one powerful tool. This is not optional. This theorem is the engine of all upcoming proofs. Read it slowly. If a prime number divides the square of a number, then it must divide the number itself. Let me explain why this is reasonable. A square is just a number multiplied by itself. A square is equal to A times A. So any prime factor appearing in A square must have come from A itself. A square cannot create a new prime out of nowhere. Think of it like DNA. If a gene appears in a child, it must have been present in the parent. This theorem will soon expose contradictions very cleanly. Now let's justify the theorem logically. Any number A can be broken into primes. A is equal to P1 times P2 times etc. times Pn. When we square it, A square is equal to P1 square times P2 square times etc. times Pn square. Notice something important. Squaring only increases the powers. It never introduces a new prime. So if a prime P divides A square, it must already be one of the primes in A. That's the entire logic. Simple, clean, and powerful. Remember this. Squares amplify primes, they don't invent them. Now we learn a new way of proving things. Sometimes direct proof is hard, so mathematicians use a clever method called contradiction. The steps are: 1. Assume the opposite of what you want to prove. 2. Use correct mathematics. 3. Reach a logical impossibility. When logic breaks, the assumption must be false. In simple words, if assuming something leads to nonsense, that thing cannot be true. All irrationality proofs in class 10 use this method. Memorize the structure, not just the steps. This is a guaranteed 3 marks proof in boards. We begin by assuming the opposite. Assume root 2 is rational. So we write root 2 is equal to a by b, where a and b are coprime. Warning: this word coprime is extremely important. Never skip it. Examiners cut marks. Now square both sides. 2 is equal to a square by b square implies a square is equal to 2b square. This means a square is even. If the square is even, the number itself must be even. So we write a is equal to 2c. This step uses Theorem 1.2. Now substitute a is equal to 2c into the equation. A square is equal to 2b square. We get 2c square is equal to 2b square implies 4c square is equal to 2b square implies b square is equal to 2c square. So b square is also even. That means b is even. Now pause. We have proved a is even, b is even. That means both share factor 2. But at the start we said a and b are coprime. This is a direct contradiction. Therefore, our assumption is false. Hence, root 2 is irrational. End the proof clearly. No extra lines. Now observe carefully. The structure does not change. Assume root 3 is equal to a by b, where GCD AB is equal to 1. Square both sides. 3b square is equal to a square. This shows a square is divisible by 3. Using Theorem 1.2, a must be divisible by 3. So write a is equal to 3c. Exactly the same pattern as root 2, only the prime changes. Substitute a is equal to 3c. 3c square is equal to 3b square implies 9c square is equal to 3b square implies b square is equal to 3c square. So b is also divisible by 3. That means both a and b share factor 3. But we assumed they are coprime. Contradiction reached. Therefore, root 3 is irrational. Examiners expect clear assumption, clear contradiction, clean conclusion. By now, you should feel comfortable. Assume root 5 is equal to a by b, where GCD AB is equal to 1. Square both sides. 5b square is equal to a square. So a square is divisible by 5. Using Theorem 1.2, a must be divisible by 5. Write a is equal to 5c. We are walking the same logical path. Substitute back. 5c square is equal to 5b square implies 25c square is equal to 5b square. So b square is also divisible by 5. That means both a and b share factor 5. But they were assumed coprime. Contradiction. Hence, root 5 is irrational. At this point, the pattern should be crystal clear. Let's summarize this powerful idea. If p is a prime number, then root p is irrational. Why? Because primes create unavoidable contradictions when assumed rational. Also remember root 4, root 9, root 16 rational, perfect squares. root 6, root 10 irrational, not perfect squares. This summary line alone can fetch multiple MCQ marks. Before moving on, ask yourself, can I reproduce the structure of these proofs without memorizing lines? If yes, you are truly ready.
This is a golden rule, but you must understand why it works. Suppose you have a rational number, clean, predictable. Now you add an irrational number, chaotic, never-ending. Can order plus chaos become order again? No. Once irrationality enters, it contaminates the result. Think of a drop of ink in clear water. Even one drop changes the entire glass. So remember this good exam-safe rule. Rational plus or minus irrational is always irrational. No exception, no trick here. Now let's prove, not guess. Assume the opposite. 5 minus square root 3 equals r, where r is rational. Rearrange. Square root 3 equals 5 minus r. Now look carefully. 5 is rational, r is rational. Rational minus rational equals rational. So the right-hand side is rational. But the left-hand side is square root 3, which we proved earlier is irrational. So we are forced to say rational equals irrational. Impossible. Therefore, our assumption is false, and 5 minus square root 3 is irrational. Notice how short and clean the proof is. Boards love this clarity. Now comes a dangerous half-truth. Many students write, rational times irrational equals irrational. This is almost correct, but not fully. The condition is very important. Rational must be non-zero. Why? Because 0 times square root 2 equals 0, and 0 is rational. So the correct rule is a non-zero rational number multiplied by an irrational number is irrational. Always mention this condition in assertion reason questions. Now let's apply the rule logically. Assume 3 square root 2 equals a over b. Now isolate the irrational part. Square root 2 equals a over 3b. Look at the right-hand side. Integers divided by integers, therefore rational. Left-hand side, square root 2, which is irrational. This is impossible. So our assumption fails. Hence, 3 square root 2 is irrational. Short proofs like this are high scoring. Now a slightly longer expression, but don't panic. Assume 3 plus 2 square root 5 equals a over b. First step, isolate the irrational part. Subtract 3 from both sides. 2 square root 5 equals a over b minus 3 equals a minus 3b over b. Now divide by 2. Square root 5 equals a minus 3b over 2b. We have successfully isolated square root 5. This algebraic discipline is very important. Now examine the equation. Square root 5 equals a minus 3b over 2b. Right-hand side, integers divided by integers, therefore rational. Left-hand side, square root 5, which is irrational. This is impossible. So our assumption fails. Hence, 3 plus 2 square root 5 is irrational. Always end with a clear concluding line. Never leave the proof hanging. This proof is short but very elegant. Assume 1 over square root 2 is rational. Take reciprocal. Square root 2 is rational. But this contradicts what we already proved. So the assumption is false. Therefore, 1 over square root 2 is irrational. Board exam tip. One-line contradiction proofs are perfectly acceptable if logic is clear. Now comes a very important warning. Students often assume irrational plus irrational equals irrational. This is false. Example, square root 2 plus minus square root 2 equals 0, and 0 is rational. So the correct understanding is operations on irrational numbers are not closed. Never generalize blindly in MCQs. Look at this carefully. In parentheses, 5 plus square root 3, close parentheses, minus square root 3. Cancel terms, equals 5. So the result is rational. Key lesson, always simplify first. Never label before simplifying. Many students lose marks by jumping to conclusions. This is a fast MCQ drill. Check one by one. Square root 4 equals 2, rational. Square root 9 equals 3, rational. Square root 1.44 equals 1.2, rational. Square root 7, not a perfect square, irrational. Golden rule. Square root of a perfect square is rational, otherwise irrational. Never be fooled just because a root symbol is present.
Now numbers disappear and letters appear, but don't change your thinking. We are asked for HCF. Rule reminder. HCF equals common factors with smallest powers. Look at x. First term has x cubed. Second has x1. So common power is x1. Now look at y. First has y squared. Second has y cubed. Smallest power is y squared. So the HCF is xy squared. Very common mistake. Taking x cubed, y cubed. That would be LCM thinking, not HCF. Letters behave exactly like prime factors. Now we switch roles from picky HCF to greedy LCM. Rule: LCM equals greatest power of each variable. For x, highest power is x cubed. For y, highest power is y cubed. So the LCM is x cubed, y cubed. That's it. No extra multiplication, no confusion. Just remember, HCF equals smallest powers, LCM equals largest powers. Now HCF becomes even stricter because we have three expressions: x squared y cubed z, x cubed y squared, x y to the fourth z squared. Check variable by variable. Variable x, powers are 2, 3, 1. Smallest is 1, so x to the 1. Variable y, powers are 3, 2, 4. Smallest is 2, so y squared. Variable z, first has z to the 1, second has no z, and third has z squared. Since one expression has no z, it is not common, so z is completely rejected. Final HCF is xy squared. Important exam line. If a variable is missing in even one term, it cannot appear in the HCF. Now find the LCM of the same three expressions. LCM asks, what is the largest version of every variable present anywhere? Check again. X, highest power is x cubed. Y, highest power is y to the fourth. Z, highest power is z squared. So the LCM is x cubed y to the fourth z squared. LCM never rejects a variable just because it is missing in one term. That's the key difference from HCF. Some students understand better with pictures, so let's visualize HCF. Imagine two circles representing two numbers. Left circle, factors of first number. Right circle, factors of second number. The overlapping part shows what they share. That overlap, and only that overlap,
gives the HCF. If a factor is not in the intersection, it is ignored. Picture this whenever HCF feels confusing. Now look at the same diagram for LCM. This time, we don't look at the overlap alone. We take everything in both circles without repeating common factors. This entire region represents the LCM. So remember, HCF equals intersection. LCM equals union. Visual memory helps reduce mistakes. This is a competency-based question, logic over speed. Given, P equals 5 times 7 times T, T not equal to 2 or 3. First, square P. P squared equals 5 squared times 7 squared times T squared. Now write 42 in prime form. 42 equals 2 times 3 times 7. Now multiply. 42p squared equals 2 times 3 times 5 squared times 7 to the third times t squared. Combine same bases. Equals 2 times 3 times 5 squared times 7 to the third times t squared. Important idea. Exponents add, they don't multiply. Many students mistakenly write 7 to the fourth. Always count carefully. Now let's revise rationalization quickly. Given 1 over 2 plus root 3, we multiply numerator and denominator by the conjugate, 2 minus root 3. So 1 over 2 plus root 3 times 2 minus root 3 over 2 minus root 3. Denominator becomes 2 plus root 3 times 2 minus root 3 equals 4 minus 3 equals 1. Final answer, 2 minus root 3. Why do we do this? To remove irrationality from the denominator. This technique is often needed in proof questions. Now a beautiful logic fact. Consider two consecutive numbers, n and n plus 1. Out of any two neighbors, one must be even. So their product, n times n plus 1, is always divisible by 2. No calculation needed, pure reasoning. This kind of logic is often tested in assertion reason questions. Here is another very important result. Consecutive numbers like 5 and 6, or 12 and 13, they never share any factor except 1. Why? Because any factor of n cannot divide n plus 1 exactly. So HCF n plus 1 equals 1. This is a favorite MCQ fact. Whenever you see consecutive numbers, write HCF equals 1 instantly.
Before class 10, you already learned something very powerful. Now we recall it properly. Take any rational number, p upon q. After simplifying, look only at the denominator. If the denominator has no prime factors except 2 and 5, then and only then the decimal terminates. Why only 2 and 5? Because 10 equals 2 times 5. All terminating decimals are built on powers of 10. The moment you see any other prime, 3, 7, 11, the decimal cannot stop. This rule is absolute, no exceptions. Let's apply the rule carefully. Given 13 upon 3125. Factorize the denominator. 3125 equals 5 to the power 5. Ask the key question. Are there any primes other than 2 or 5? No. So we can write 3125 equals 2 to the power 0 times 5 to the power 5. Hence the decimal terminates. Important note, the numerator does not matter for termination. Only the denominator decides. Now check. 23 upon 200. Factorize 200 smartly. 200 equals 8 times 25 equals 2 to the power 3 times 5 to the power 2. Again, only 2 and 5. So this decimal terminates. Very common mistake. Students see a big number and assume non-terminating. Never assume. Always factorize the denominator. Now look at 71 upon 99. Factorize 99. 99 equals 9 times 11 equals 3 square times 11. Here we see prime 3, prime 11. These are not allowed for termination. So the decimal expansion is non-terminating repeating. Board exam language matters. Don't just say non-terminating. Say non-terminating repeating. That wording is important. This is a thinking-based MCQ. We test smartly instead of proving blindly. Try odd numbers. 3 square minus 1 equals 9 minus 1 equals 8. Both divisible by 8. Now try even numbers. 4 square minus 1 equals 15, not divisible by 8. So pattern emerges. When n is odd, n square minus 1 is divisible by 8. This kind of question rewards pattern recognition. This problem mixes algebra with number theory. Given L plus H equals 1260. L equals H plus 1000. Substitute H plus 900 equals 1260. That is 2H equals 360. Implies H equals 180. Then L equals 180 plus 900 equals 1080. Now use the duo rule. Product of numbers equals H times L equals 180 times 1080, that is 194400. Key lesson. Find HCF and LCM first, then the product. Never panic when algebra appears. First find the actual HCF. HCF of 65 and 117 equals 13. Now equate. 65m minus 117 equals 13. Solve. 65m equals 130 implies m equals 2. Rule. Always compute real HCF first, then match the expression. Question. Find the exponent of 5 in 3750. Break carefully. 3750 equals 375 times 10. Now, 10 gives 15. 375 equals 3 times 125, that is 5 to the power 3. Total power of 5 is 1 plus 3 equals 4. Always count how many times the prime appears, not digits. First simplify. Root 20 equals root 4 times 5 equals 2 root 5. Question. What is the smallest irrational number to multiply so the result is rational? Answer. 2 root 5 times root 5 equals 2 times 5 equals 10. So, the required irrational number is root 5. Always simplify before deciding. Vocabulary check. Very common MCQ. Smallest prime number equals 2. Smallest composite number equals 4. Now find HCF of 2 and 4 equals 2. This question tests definition of prime, definition of composite, basic HCF logic. Easy mark. Don't miss it.
Assertion reason questions are logic tests, not memory tests. Read the assertion. Root 7 is irrational. This is true because 7 is prime. Now read the reason. Square root of any prime number is irrational. Also true. Next, and this is the key step, ask, does the reason explain the assertion? Yes. Because 7 is prime, its square root must be irrational. So, the correct option is A. Both A and R are true, and R explains A. Never rush AR questions. Always check truth plus explanation in that order. Let's analyze calmly. Assertion. 13915 is composite. Reason. It is written as a product of primes. This is exactly the definition of a composite number. So, again, A is true, R is true, and R correctly explains A. Correct answer, A. Notice something important. Assertion reason questions often hide definitions inside the reason. This is a classic trap. Assertion. HCF of ABC times LCM of ABC equals ABC. This is false. The product rule only works for two numbers. Reason. The rule works for two numbers is true. So we have assertion is false, reason is true. Correct option, D. Remember, one wrong assumption can flip the entire answer in AR questions. This is a case study format, but the logic is familiar. We want same number per room, minimum number of rooms. To minimize rooms, we must maximize participants per room. That means HCF. HCF of 60, 84, and 108 is 12. Now divide. 60 divided by 12 equals 5. 84 divided by 12 equals 7. 108 divided by 12 equals 9. Total rooms? 5 plus 7 plus 9 equals 21. Case studies look long, but they are just two-step logic problems. Here, the language changes. We want the minimum number of books so that both classes can be distributed equally. Minimum plus together equals LCM. LCM of 32 and 36 equals 288. So the library needs 288 books. Always underline words like minimum, maximum, together, equally. They decide the method. This slide is about how you write, not just what you know. In irrationality proofs, always write A and B are co-prime. Why is this essential? Because the contradiction depends on it. If you forget this word, logic collapses and the examiner cuts marks. Good mathematics is precise communication. Before submitting your paper, do sanity checks. Always verify, does HCF divide LCM? Is LCM greater than or equal to the numbers? If HCF equals 12, LCM equals 15, that's impossible. These 10-second checks can save 4 to 5 marks lost to silly mistakes. This is your mental map. Before solving any problem, ask, which box does this problem belong to? If you identify the box correctly, the math becomes easy. This table alone can guide you through the entire chapter. Before the exam, check yourself honestly. Ask, can I factorize confidently? Can I decide HCF versus LCM without hesitation? Can I reproduce root 2 proof without memorizing lines? If yes, you're safe. If not, this is the chapter to fix first. We've reached the end of Chapter 1. This chapter is not about difficulty, it is about discipline. Disciplined thinking, disciplined writing, and disciplined logic. If you master real numbers, you don't just score marks, you gain mathematical confidence. Practice regularly, trust logic over shortcuts. We'll meet next in polynomials, standing on this strong foundation.